Well, hi, and welcome back to our GradStats 2024 Lab series. For Lab 7 in JASP, we're working with T-tests. And again, a T-test is used when we want to compare the averages of a continuous outcome variable between two things. What two things? It could be two different groups. It could be two occurrences like time points. It could be between matched pairs, or even between a sample and a population. And what a t-test result tells us is the difference between those two things a significant difference or not? So for our lab, we'll be running an independent samples t-test and a paired samples t-test. And the materials you'll need are linked in the description, include the two data sets, and the lab sheet for Lab 7 for SPSS, because we'll look at it for write-ups. So grab those things and we will get started. So with our independent samples t-test, this would be a research question that looks at, are there significant differences between two independent groups? Our research question for this first part of the lab is there a significant difference in average self-esteem scores between men and women? So we'll open up our survey.sav data set wherever you've placed it. And the first thing we do is take a look around, make sure everything came in correctly, that our ID variable is nominal, our variables that are categorical are indicated so, and continuous variables are set correctly, right? And then we want to describe some of these variables. We have the variables that will be going into the model, but we also might want to grab some descriptive variables for just helping explain the context of the data set as you're working over introducing your reader to the data set, what's it about, and like a sample description. But you do eventually want to get to the variables of interest, the ones that are going into the model for answering this research question, which would be self-esteem and sex, the gender variable. So do some looking around, make sure that you have enough information to describe your data set well to your reader, but then you're going to move on to focusing on your variables of interest. So first, let's take a look at our sex variable. Now, as usual, JASP is going to start giving us very quantitative information, like as if this variable is continuous, but we don't need most of this stuff. We don't need mean, standard deviation, min and max, because it's a categorical variable of just male and female. But what we do need is the frequency table at the bottom there. So turning on frequency table, now that's the kind of information that we're going to need for the write-up in terms of our variable of interest, because this is one of the variables going into the t-test model. We know how many males and what percent of the whole they represent. Same thing for females. And then that's the information we're starting with when we narrow down to our constructs. We're going to need somewhere or even more information for our continuous variable. So we'll grab another descriptives panel, and this will be descriptives for total self-esteem, which is our continuous outcome. So let's get that guy, he's near the bottom right there, and put him into the variables box. So this is good information we need. We need to know the mean and the standard deviation of that outcome variable overall. We also want to know if it's normally distributed. So this is one of those assumption checks that we do when we have a continuous variable. So let's first take a look at the histogram. First take a visual look at it. In basic plots, we'll go to distribution plots. And yeah, that is not looking very normally distributed. That's got a very strong negative skew. I am not expecting a non-significant Shapiro-Wilks here. So let's go check out some of our other numbers. In our statistics side panel here, we can ask for skewness and kurtosis and let the system fill that in. So yeah, a negative 0.8 skewness, that makes sense. Look how powerful that negative skew is. Kurtosis, not as bad. And how about our Shapiro-Wilk test? Yep, significant. So visually and by the numbers, looks like we have a violation of univariate normality for total self-esteem. Okay, but we also want to know, like, this information we need. We need the mean, we need the standard deviation, we need to know what self-esteem is doing as a whole. But as we're looking at a t-test with two separate groups, we also want to know about the distribution of self-esteem by group. Like, what is the distribution of self-esteem for males? And what is the distribution of self-esteem for females? So to do this, we're going to go up to this green item where it says duplicate this analysis so that we keep this information because we need this. And now let's say this one's going to be descriptives for self-esteem by sex. We'll get a little more detail on this one. We already have the same information that we had before, but now we're going to go over here and grab the sex variable, our grouping variable, and put it down here in the split area. And as it updates, we see now our mean and standard deviation for self-esteem across the male group and across the female group. We even have our distribution plots for males and females. Still looks pretty negative skew, right? And then even our p-value for Shapiro-Wilks is significant for both of those distributions. So we definitely have a violation of univariate normality for our outcome variable of total self-esteem. Going on from there, we're going to want to do our t-test. So I can go ahead and close these and get a independent samples t-test out of the classical area. In here, my dependent variable is total self-esteem, and my grouping variable is sex. So I can go ahead and start filling in that information. And it will start populating the results. So far I have a t-test of 1.62 degrees of freedom and p-value indicating there's not a significant difference here. See what I mean? With a p-value that's not less than 0.05, we're seeing that the difference between these two groups is not significant. Well, what difference? Let's grab the descriptives, which will tell us again, the average, the mean, and the standard deviation. We can see that they differed by, 1 point? I can see why that would be non-significant difference, right? And then we're also going to need the effect size here. Cohen's d at 0.157. And according to our cutoffs, right here, a Cohen's d of 0.2 is small. And we have a Cohen's d of 0.16. So it's less than small, which makes sense with our non-significant t-test. But right now, we still have not checked one of the other assumptions for t-test, and that's the homogeneity of variance using Levene's test. We can get that by going into the bottom where it says assumption checks, equality of variances, and Levene's. So now we have Levene's test on this table in the middle. It says that the significance was 0.06, which is not significant. And when we're doing assumption tests, a non-significant result means we did not violate the assumption. Which assumption? The homogeneity of variance assumption. So we're good on that. It is a non-significant test, and we have our effect size. So let's take a look at our write-up so far. We want to let the reader know what test was conducted and what it was about, like what variables are in it. We let the reader know about our check of assumptions in terms of the normality issue. And we let the reader know the results of the test. The difference was not significant, and there's my t-stats line. In other words, no significant practical differences in self-esteem between males and females. So all of that information we were able to get out of the results so far, like the mean and SD for each male and female group, our t-test, our degrees of freedom, our significance value, and our effect size. What we could use still is some graphics. We can look at bar plots. Looks kind of like this. And while you can turn off the fixed horizontal axis to 0, see what it does? It kind of makes it look super big difference when there's only like a 1.5 point difference there that's not even significant. So I'd be careful with that. You always want your graphics to be transparent and true. You don't want to mislead someone looking at the graphic to make assumptions or make it imply that there was a big difference between these groups if there really wasn't. So watch out with that. We also can look back at this descriptives of self-esteem by sex and be able to look at some plots here, like the box plots. I went into customizable plots, and it's just updating that. So then we have a nice little side-by-side box plot on the score of self-esteem for males and the score for females. So those are a couple of ways to get some nice plots that could go with your write-up. So that's for our independent samples t-test. To look at our next part, the paired samples t-test, we need a different data set. You'll go back to your menu and open and browse to where you have the experim.sav data set. And it's going to open up a whole nother window. JASP won't do two data sets in the same occurrence, so it's going to have a second JASP occurrence opened up here. And as usual, we want to look over the import and make sure it's correct. Like we have sex as a grouping or as a categorical variable, group, which class the students were in as a categorical variable. The rest of these are pretty much continuous except for these last three. But here on ID, it recognized it as a scale, but we know that it's just the unique identifier, so we need to turn that to nominal. Cool. Now our question for this part 2 is there a significant change in participants' fear of statistics test scores following participation in an intervention. Now, again, I look at the code book, I try to get familiar with the data set so that I can have a beginning paragraph normally that would help introduce the reader to what is this data set about. This one is looking at a before and after intervention, testing someone's fear of statistics, their confidence, and their depression values. So looking at measures along the way, so repeated measures. And that's what you need for a paired samples t-test, is 2 occurrences of the same person. Okay, so let's take a look at what we have here. When we go into descriptives, again, you want to collect some descriptives about your sample so that you can talk to the reader about the sample. But you do want to get down to narrowing to the variables you're actually interested in. And to answer our paired samples question, we want to know about FOST1 and FOST2, which is fear of statistics at time 1 and fear of statistics score at time 2. And we'll drop those into our variables area. And we already start getting some great information here. The mean and the standard deviation at time 1 and time 2. We can see there's a difference, 40 and 37, about 2.5 points different. Is it a significance difference? We don't know yet. But some of our first checks, our first preliminary assumption checks, especially when we have continuous variables like these, is are they normally distributed? Again, we can go into our basic plots and turn on distribution plots to see their histograms. Yeah, I would think FOST1 might look okay. FOST2 looks kind of weird. So let's check our other numbers, like visual inspection. Let's go check our other numbers as well. Back to our statistics fold down, and let's look at skewness and kurtosis. Looks like we have negative skew and a kind of flat kind of kurtosis there. How about our Shapiro-Wilks test? The p-value or significance value of Shapiro-Wilks are both over 0.05. So according to Shapiro-Wilks, this is the univariate normality check has been met. So let your reader know what your visual inspection is and what the Shapiro-Wilks results are. Okay. So another assumption test we would do for a paired samples t-test like this is finding out if the difference between the time 1 measure and the time 2 measure is also equally distributed. Now, we don't have an easy way of getting to that here, but we will get that in the actual paired t-test area. So let's go on to that. We'll go to t-test, paired samples t-test. And here we want to put our variable pair of FOST1 and FOST2 into our variable pairs area. It already starts filling in our information. We have the t-test is 5.39, degrees of freedom 29, and it says that it is a significant difference between time 1 and time 2. Now, one thing we want to get here is our effect size. So there's our Cohen's d at 0.985, and that would be considered, according to our little cutoffs, 0.985 is large. So that's a large effect of the difference between time 1 and time 2 from that intervention between. Now, there's a significant difference here, but which way? Like, which one is higher or lower? Well, we can get descriptives. Looking at this table, we see that at time 1, the fear of statistics score was 40.2, compared to at time 2, the fear of statistics score was 37.5. So there's a difference, and according to our t-test, it's a significant difference. So let's see what this looks like in terms of bar plots. Okay, we have a little bit of difference. If I turn off that, it looks bigger, right? So I usually try to not make it look overstated in my graphics because I don't want to mislead anyone. And then what else do we need? The other assumption check here is the difference between FOST1 and FOST2. Is that normally distributed? So we're not going to make a new variable here because we already have the ability in the panel to just check for normality in the assumption checks. And it added this middle area of FOST1 minus FOST2, so the difference, and we're doing a test of normality with the Shapiro-Wilks test. So we see that it's 0.052. It squeaks by. It's a non-significant Shapiro-Wilks test, just barely, but it does meet normality here. So we've checked our assumptions for the paired test. We've got our information we need with the t-test, the degrees of freedom, the significance value, and the Cohen's d. Let's take a look at the write-up for this one. A paired samples t-test was conducted to evaluate the differences in 30 students' fear of statistics scores from before the intervention and after the intervention. So that's a good place to give your reader the details as far as the summary statistics for those continuous variables of fear of statistics at time 1 and fear of statistics at time 2. You let your reader know if there's a figure. Let the reader know what you did as far as checking assumptions. Shapiro-Wilks test was non-significant. And let your reader know the results of your test, including your stats line. Now that Cohen's d is large, so a interpretive sentence about the large effect size would make sense here. And then we can use our bar plot that we made to help the reader see what we're talking about. Okay, that is it for our paired samples t-test here. So we did a lot with the lab. We ran 2 types of t-tests, an independent samples and a paired samples. We checked a lot of assumptions that are kind of new to us because these are the ones specific to t-tests. And we were able to pick out information in our output to put into the write-up and explain what we found to the reader. So have fun with that, and I look forward to seeing you at the next lab.